All right, exponent rules part 4. We're going to talk about actually roots and radicals in this section. So you've seen the symbol before. We've talked a little bit about it this year. I think that square root idea. And these are going to start off pretty simple. Square root of 9, you know, is 3 because 3 times 3 is 9. Square root of 144 is 12 because 12 times 12 is 144. Square root of 49 is 7. Square root of 10,000. How do we do powers of 10? Well, look at those groupings of zeros. 2 zeros, 2 zeros. There's 4 zeros. That means its square root should have 2 zeros. So an even number of zeros is really easy to find out for us. That square root, why do we look at square roots under these exponent rules? Square roots actually follow the same rules as exponents. The square root of a is the same as saying a to the 1/2 power. It's a fractional exponent. We're not going to do too much with these this year. I just want to touch on them so you've seen them. Basic square roots we know. Our rule is that the square root of a number is the number that when you multiply it by itself gets you back to the original number. You know that. So what about these other symbols in the next column? Now, a thing to note in that first column is that this is one of those understood things that people in math, everybody knows, nobody writes it. So like if I gave you x, you know, everybody knows that there's a 1 in front of that x. We just don't write it in. Everybody knows it, we don't write it. This square root idea is kind of the same thing. Everybody in the whole math world knows that there's really a little 2. It's understood that we're taking the second root, which means I multiply 2 things together to get that value. That's where that denominator of 1/2 comes from. If I look at other radicals, that symbol is called the radical. That's the radical. And that little number is called the index of the radical. Again, if there's nothing written, it's understood that it's a 2 and we're looking for a square root. But if there's another number written there, what we're looking for is a number that times itself that many times. That index number of times gives us that original number. So let me start with the 8. The cube root of 8. Is there a number that multiplied by itself 3 times gives us 8? Well, yeah, that's 2. 2 times 2 times 2 is 8. So what I'm looking for here is there a perfect group of 3 of those things to give me 8? Yeah, so my answer would be 2. That's the cube root of 2. 625, well, let's see. Here's what I know about 625. It happens to be 5 4 times. There's a perfect group of 4 5s, so the fourth root of 625 would be 5. We don't need to memorize many of these. I just want you to know that symbol. Cube root of 27, well, let's see. The cube root of 27, 3 times 3 times 3 is 27. The cube root of 27 would be 3. Again, with a power of 10 up at the top, how many zeros do we have here? 1, 2, 3, 4, 5 zeros. And oh, I'm looking for the fifth root. 5 zeros means 10 to the 5th power. The fifth root of 10 to the 5th would be 10. So our rule here is we're looking for a group of this number of factors to get us to this number. I don't know how I'm going to say that in words. I guess algebraically I could say if that A is equal to the product of a bunch of things, so let's say B times itself n times, then the nth root of A would be B. That's kind of weird, right? So you're looking for a group of the same number of things that many times. All right, I Googled the definition. Google gave me the nth root used n times in a multiplication gives the original value. Again, we're not going to focus on this. We do not have time this year, but if you ever run across that symbol, that's what it means. This is another idea. This is called simplifying radicals. Now, these are not perfect radicals. In a normal year, we'd spend quite a bit of time on this because it does come up a lot in geometry. We don't have a lot of time this year. I'm just going to show you some simple examples. We could find square root approximations. We've talked about that. Square root of 28 is a little bigger than the square root of 25, so a little bit more than 5, maybe 5.1, 5.2. Square root of 72 is between the square root of 64 and 81, somewhere in the middle there, closer to one than the other, but probably about 6.4, 6.5, somewhere in that area. That's not what we're looking for here. What we're looking to do is what we call simplifying radicals. Everybody has a different way to do this. I'm going to show you the way I like to think of this. What we're going to do is we're going to factor tree these numbers. 28, remember old factor trees, our good friends factor trees from elementary school? They come back again. 28 is 4 times 7, 2 times 2 times 7. So square root of 28 is the same as the square root of 2 times 2 times 7. Now what I'm looking for, because this is a square root, is, remember there's that little index of 2 there, I'm looking for any perfect group of 2. Any group of 2 means I've got a perfect square. The square root of 2 times 2 is the square root of 4, that's 2. Any group of 2 of the same thing means I have a whole number. I have a perfect square. I can pull that outside. So what we do is make that the whole number 2 times whatever's left over. What's left is the square root of 7. This is what's considered the radical in simplest form. Let's do the same thing for 72. So 72 is 9 times 8. 9 is 3 times 3. 8 is 4 times 2. And 4 is 2 times 2. So square root of 72, if I prime factor that, is 3 times 3 times 2 times 2 times 2. And again, I'm looking for any groups of 2 of the same thing. 2 of the same things means I have a perfect square. Square root of 3 times 3, that's the square root of 9, that's 3. I can pull that outside. Square root of 2 times 2 is the square root of 4, that's 2. I can pull that outside. Again, with these, I've mentioned this before, no addition, subtraction, everything here is multiplied. So when I pull out the 3 and the 2, they're multiplied together. And then what's left over? A square root of 2. So in simplest form, we would say 3 times 2 is 6 times the square root of 2. Square root of 45, well, that's 5 times 9. 9 is 3 times 3. Square root of 45 is 5 times 3 times 3. Any group of 2 makes a perfect square. Square root of 3 times 3, square root of 9 is 3. What's left over? That 5. So again, my phrase, the way I think of these is any group of 2, I pull one of them outside. Square root of 35, well, that's square root of 5 times 7. There's no group of 2 of the same thing. That means square root of 35 can't be simplified. It's already in its simplest form as square root of 35. Square root of 48. Now, if you recognize that 48 is 16 times 3, go right ahead and think of it as the square root of 16 times 3. The square root of 16 is 4. Left over square root of 3. But if you want to keep going, that's fine. 4 times 4, 2 times 2, 2 times 2. So square root of 2 times 2 times 2 times 2 times 3. Any group of 2, I pull one of them outside. Well, I have 2 groups of 2 of the same thing. 2 2's come out. 3 stays inside, so 4 square root of 3. We get there either way. So again, you'll see that next year in geometry, not a huge deal, but know that it's out there and it's not a hard thing to do. This other column, real quickly, is just another way of writing these exponents. I'm just going to touch on it briefly so you've seen it. The base is here. We can write this with an exponent as 5 to the numerator over denominator. That's the same as 5 to the 2/3 power. This would be base of 3. Numerator is the exponent. The denominator is the index of that radical. I could go backwards here. That's the 7th root of 10 to the 11th power. 4th root of 3, 3rd root of 4 to the 3rd would be 4 to the 3 over 3, or just 4 to the 1st power. This would be index of 3, base of 5, exponent of 4. So no big deal here. I just want you, again, we're not going to spend any time on these other than right now. You've seen them now. So this would be 2 to the 6 over 3, also known as 2 to the 2nd, or just 4 if you want to keep going. A to the m, the nth root of that would be a to the m over n. We're going to pause here.